Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 15th, 2025, about 2 days ago. This paper introduces RoboTracer, a three-dimensional aware vision language model for robots that hits about 79% average success, and it beats Gemini 2.5 Pro by about 36% accuracy on Trace Spatial Bench. The paper is titled RoboTracer, Mastering Spatial Trace with Reasoning in Vision Language Models for Robotics. Alright, the interesting part is how it mixes scale-aware supervision with metric-sensitive reinforcement fine-tuning to get reliable multi-step spatial traces. Also, the authors shared an official GitHub repo for RoboTracer. Right now you will find the core project scaffolding with the README, assets, and an overview of the RoboTracer model and the Trace Spatial dataset pipeline. The README also lays out a release timeline for evaluation code, trained 2B and 8B models, and training and data generation code. Figure 1 explains what spatial tracing means in practice, because a robot has to turn a natural language instruction into a precise three-dimensional path. The full figure lays out the pipeline from language to actions, and it highlights two key skills. The left panels show three-dimensional spatial referring and measuring, meaning the model must both point to the right objects and estimate real-world distances. The middle and right panels show the resulting trace and how it supports safe, collision-free robot motion. Figure 2 explains how RoboTracer turns an image plus an instruction into a metric three-dimensional path that a robot can follow. The full diagram lays out the end-to-end pipeline so you can see where geometry and scale get injected. The left side shows supervised fine-tuning, where a scale decoder learns a real-world scale factor. The right side shows reinforcement fine-tuning, which adds metric-sensitive process rewards that check intermediate referring and measuring steps. Table 1 shows that the scale-aware supervised fine-tuning setup translates into better spatial understanding and measuring across many benchmarks. This full table compares multiple vision language models, and it reports top 1 and top 2 success rates, which means the model gets credit if the correct answer is ranked first or second. The bottom two rows highlight RoboTracer, and the 8B model posts about 97% on several spatial understanding columns. The rightmost measuring columns also jump, with about 83% on scale estimation. Table 4 makes the key point that getting depth and scale right is what separates good-looking two-dimensional traces from truly usable three-dimensional robot paths. This table summarizes Trace Spatial Bench, where a run only counts if the start and end are correct, and the middle of the path avoids collisions, so depth mistakes really hurt. The bottom block shows RoboTracer with reinforcement fine-tuning improving overall to about 45, when it also uses intrinsics and absolute depth and process rewards. Okay, two takeaways stand out. RoboTracer treats scale as a first-class prediction problem, so its traces live in real three-dimensional units, and the metric-sensitive reinforcement fine-tuning rewards the right intermediate steps, so multi-step paths stay accurate and collision-aware. The broader implication is that vision language models can become practical robot planners when geometry and learning signals match the physical world. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.